Hey everyone, welcome back. Now, like I said, honestly, the best way to learn this is actually to do it. So before I jump into what I'm going to call the true example problems, I'm going to show you some of the examples that are shown in the book. And we're just going to go over why they do things and what they're doing. So what we have here is a 10-inch diameter steel sphere, right there. Why is steel yellow? I don't know. And it's anchored firmly to the top of the 12-inch square concrete pedestal. This is some weird like new age art here. Since it's securely fastened, that means they act as one member. They're going to have a center of gravity that's from both of them connected. The pedestal is 18 inches high. And we want to get the center of gravity of this built-in member. Now we're going to have to look at Appendix G to find the densities, which I'll go ahead and show you. So the density of steel is 490 pounds per foot cubed, and the density of concrete is 150 pounds per foot cubed. And you're going to get that from the appendix. So be looking for it. Okay, now to solve for our center of gravity, remember we have that equation, okay? X bar is going to equal the sum of the individual weights times their little x location, which is usually x squiggly, over the total weight. And y bar is equal to sum of the weight times their y, the centroid, over the total weight. But if you look at this, in the z bar, so there's 3 dimensions here, is equal to sum of the weight times their z location all over the total weight. If you look at this in the z direction and the x direction, this thing is symmetric. It doesn't actually change. If I look at it from the front, this is perfectly symmetric. So what that tells me is that since I've got this axis of symmetry, my centroid is going to be somewhere along that axis. I don't know where it is. It's going to be up here or down here, but it's somewhere on the axis, which means that I don't have to worry about these two. Don't have to care about them all because they're taken care of by the fact that there is this nice axis of symmetry right through the origin along the y-axis. So effectively what it tells me is that x bar is going to be equal to 0 and z bar is going to equal to 0 as well. So I've got to find this y bar. Okay. Now to do that, first off I need the centroid of both of these shapes, which luckily for me, the centroid of a sphere and the center of gravity of a nice big cube is right at their center. So it'll be half the distance from here, and this one will be half the distance from the bottom. So that'll be 9 inches up, and this one will be 18 plus half of 10, so that'll be 23 inches up. You have to go from the same point, just like when you were doing those resultant moment vectors. Okay, so I got my little y squigglies. Now what about their weight? Well, their weight is going to be equal to their volume times density. So weight is going to be equal to their volume, technically times their specific weight. But if you want to call this density, you could. And so that's going to be equal to, for the sphere, well, that's going to be 4/3 pi r cubed. That is the volume of a sphere. It's going to be times 490 pounds per foot cubed. 490 pounds per foot cubed. And then if I plug all that in, so I plug in my radius, which is going to be 5 inches. So I get 4/3 pi times 5 inches cubed. All that multiplied by 490 pounds per foot cubed. But here's an issue you need to see. This is inches, that's feet. So we need to convert. So I'm going to go ahead and multiply by my conversion, which is going to be 1 foot is 12 inches, and I have to do that 3 times because it's cubed. And if I do that, I get a weight of, 148.5 pounds. Okay, so that's right here. I'll make that right there, 148.5 pounds. Perfectamundo. Okay, dragging it around, and let's see, there. Now let's see if I can find this second weight. Well, it's just the weight of a box, so the volume is pretty easy. So weight is going to be equal to my volume times my specific weight. It's going to be equal to the volume of the box, which is going to be 12 times 12 times 18. Remembering that all these are inches. Times the specific weight, which was 150 pounds per foot cubed. And since this is inches and this is feet cubed, I have to convert. So I'm going to multiply by 1 foot over 12 inches. That's cubed, so I have to do it 3 times. If I multiply all that out, what do I get? I get that the weight is going to be equal to 225 pounds. Which gives me a total weight, my big W, is going to be equal to 148.5 plus 225, which is just around 374 pounds. Okay. So with this, I should be able to solve. I have everything I need for this equation. So let's try that out and see if we can solve. Okay. So y bar is going to be equal to the sum of the weights times their centroid, measured from the same place. The centroid has to be measured from the same place. You can't just say from the edge of the object. It's got to be from the origin or some just connected point. And so that's going to be equal to, well, the weight of the steel sphere, which is 148.5, times the distance to its centroid, which is 23 inches, plus the weight of the concrete slab, which is 225 pounds, times the distance to its centroid, which is 9 inches, plus those coming from my origin at the bottom. I'm going to divide that by my total weight. And what I get is that my centroid would be equal to 14.55 inches. So it's somewhere in the middle, right around here-ish. And it's a little bit closer to the centroid of the concrete block because the concrete block was a lot heavier. And so that is my answer. I'm done. And it's the same equation which you have seen a whole bunch of times. We're going to use that equation over and over and over and over and over again. So master it. Make sure that you can do this weighted average equation all the time. Well, thank you for listening, everyone. And I'll see you all next time as we do a few more examples to really drive home how you use these equations before I actually do some true example problems. See you later. Bye-bye.